Welcome to Make Made Simple. Today we will be studying forces defined by its magnitude and 2 points on its line of action. What this means is that I have a force F here, which this is our x, y, and z axis. First, I'll tell you is our x, y, and z axis. So this is our x, this is our y, and this is our z-axis. Now I have made a box parallel to the x-axis. The x-axis line is here, the y-axis is here, and the z-axis is here. Now this is a force F. This is a force F who is going from point here to here. So I'll just write those 2 points. Those 2 points are M and N, whose coordinates are x1, y1, z1, and x2, y2, z2. So these are our 2 points M, x1, y1, z1, and M, N, x2, y2, z2. And this is our origin O here. So what's next is we can define this Mn vector. This is Mn vector, and we can say that this unit vector, just a small portion of this would be lambda. So this small vector is lambda. This big vector is F, going from point M to point N. Then we have dx equals to x2 minus x1 dy equals to y2 minus y1 and dz equals z2 minus z1. So these are our three vectors, uh, uh, three chord three vectors whose magnitude is dx, dy, and dz. So we have our force vector F here. We can write Mn vector as we can write Mn vector Now we have understood this coordinate is x, y, and z. So I'll just rub this down. I'll just make it here a little smaller so that everybody understands. This is our y, this is our x, this is our x, this is our y, and this is our z. So after that we will write mn vector. Mn vector is equals to dx I cap plus dy j cap plus dz k cap. Now after this we will write we have our unit vector lambda is equals to we have unit vector lambda equals to lambda equals to mn vector by mn, that is 1 by d. D is this distance from here to here. So d 1 by d is dx I cap plus dy j cap plus dz k cap. So this is lambda. This is our lambda unit vector which I have written from here to here. This portion is lambda. So that we have found out. Now we know that f vector is a product of f magnitude f and lambda. So I'll write it here. F vector is a product of the scalar f and the vector lambda. Then f vector is equals to f lambda. F vector equals to f lambda equals f by d dx I cap. I'll write in the bracket this lambda vector dx I cap plus dy j cap plus dz k cap. So This is our f vector. Now we can say that fx, the component of x, f in the x direction would be equal to, our f vector is this, then fx equals fx equals f dx by d, f dx by d, fy equals f dy by and fz equals f dz by d. And this dx, dy, dz, what are these? These are this which I have written in red. Dx is equal to x2 minus x1, dy is equal to y2 minus y1, and dz is equal to z2 minus z1. So these are our three quantities. So f vector has been resolved into its components fx, fy, and fz. And if we want to find out what is d, then d would be root under of dx whole square plus dy whole square plus dz whole square. Now what are the direction cosines of force F? So direction cosines of force F from equation 2, this is our equation 2, this one, I'll put it as 1 from equation 1. From here we can say that dx is equals to d lambda, or we can say that dx cos theta is equals to dx by d. Dx is equals to, we know that dx is equals to d cos theta x. This we know that this, if I put this here from x axis theta x, and similarly there would be an angle theta y from the y axis and theta z from the z axis. So we know that dx is equals to d cos theta, then cos theta would be equal to cos theta x equals to dx by d cos theta y equals dy by d and cos theta z equals dz by d. So these are our three relation direction cosines of force F. Cos theta x is equal to dx by d, cos theta y is equals to dy by d, and cos theta z is equals to dz by g. So that was for the direction cosines of force F. Now I hope you have written this down. I'll rub this portion here. Please write all these in your notes. These are very important relations. So yeah, you can pause the video and note them down. Okay. Now we have at 2.4 section. We were studying 2.4b section. Now we will study 2.4c. 2.4c is addition of concurrent forces in space. So we know that r vector is equal to summation of r vector is equals to summation of f. Summation of f vector. Resolving r and f into rectangular components, we have resolving r and f vector into rectangular components. We have r vector I cap, rx I cap, ry j cap plus rz k cap equals summation of fx I cap, fy j cap, and y j cap plus fz k cap. So now if we take the summation inside, it would be summation fx I cap. So rectangular components of the resultant are rectangular components Rx is equals to summation fx, Ry is equal to summation fy, and Rz is equal to summation fz. I can write this here. Rx is equal to summation fx, Ry is equals to summation fy, and Rz equals summation fz. And the resultant of concurrent forces in space, what would be the R? R vector would simply be R vector, or we can say R vector is resultant of concurrent forces in space. So these are our three relations. Then resultant of concurrent forces in space. Resultant of concurrent forces in space is equals to R vector equals under Rx square plus Ry square plus Rz square, and cos theta x equals Rx by R cos theta y equals Ry by R cos theta z equals to R z by R. So this is the resultant of concurrent forces in space. Concurrent means that the forces in space are having a common point P. Suppose I have drawn, if I would have drawn three forces with the same point P, like this, one force, 2 force, 3 force. These three forces are having a single common point P, so that is called a concurrent point. So for a resultant of concurrent forces in space, we have r vector is equal to rx square plus ry square is equal to rz square, and cos theta x is equal to rx by r, cos theta y is equal to ry by r, and cos theta z is equal to rz by r. So that was all for today. I hope you have liked the video. If you have gained some knowledge from this video, please do like the video and subscribe to my channel and share it among your friends. Thank you.